So let's carry out our discussion. I would like to, before getting into more into it, I would like to really discuss one thing, that sometimes for sine inverse x, there is also a notation used which is like arc sine x actually. Okay, so this is also a notation. For cos inverse x, there is a notation you call the arc cosine x. Okay, why you call them arc sine x and arc cosine x actually? I mean, if you remember, I just quickly can go actually back. For example, if you have a sine, so for example, sinusoidal function that goes like that actually. Okay, then the inverse of a function, okay, the inverse of this function is really a one small arc in it. So what do you mean by arc? Arc is really, a curved segment. Okay, so a small curved segment. So out of this entire function, only this arc of the sine function is really the inverse sine function actually. So therefore you call it the arc sine x. So take your sine x, okay, function, but this arc, this piece of what do you call segment of the function sine x is really the inverse sine x. So therefore some people also like to call it arc sine x actually. So whenever when you see, for example, in your exercises and examples, you see arc sine x, you mean sine inverse x actually. And this is a natural name given to it, that okay, you take sine x and then take the appropriate arc of it, that is a function, okay, which must be a function actually. So you can take this arc or this arc, any arc, but what is a function, then that arc is really that arc of sine x, okay, the part of the sine x is really the sine inverse x actually. Okay, so therefore some people also use, or in exercises you will also find the notation sine inverse x, and therefore you call it arc sine x and arc cos x and so on and so forth. How about tangent x? Is tan inverse of x are arc tangent x. Okay, I mean, if you remember that the graph of tangent function is really interesting actually. Okay, so if you take, for example, any interval of the length pi, okay, of length pi, so for example this is 0 and pi by 2 and pi and say 3 pi by 2 and so on and so forth, and you take, for example, minus pi by 2 and you see, say, pi by 2 to 3 pi by 2, so it's going to be negative 3 pi by 2 and say minus pi and so on and so forth. Take any interval of length pi, okay, take any interval of length, take any interval. So for example, I am focusing on this interval actually, okay. So when you will plot your sine function, you will see that actually you are, no, this actually, okay, I should take minus pi by 2 to pi by 2 is going to be a pi. So if you're going to look at the graph of the tangent x here, okay, and we know that tangent x is sine x by x. So sine x at 0 is 0. So 0 by cos x is going to be 0. Okay. So this graph goes like that. So it starts from 0, and this pi by 2 is really an asymptote. So x equal to pi by 2 is really an asymptote for tangent x actually. Okay. And you're going to have the same. Okay. You can take say another, what do you call, a piece of length pi, so you're going to get the same. So sin pi is 0. So you're going to get all such kind of what do you call graphs always actually. So this is not just going to be one graph, but the graph of the tangent is going to look like similar kind of things. Okay. So if I redraw it clearly, okay. So if it is say, so you're going to see that it's going to be a series of graphs actually, which is going to be like that. Okay, something like that. Okay, I'm bad at drawing, but so you can look at it in Desmos and you'll see that you're going to have it actually. Okay, so this is really going to be between minus pi by 2 to pi by 2 and so on and so forth. Now, this is my x-axis and this is my y-axis. So is it a function? The answer is yes. For every single x you have a unique output, so it's a function. What if I give this guy name x and this guy name y actually? Now the trouble is, for one x you have infinity many values of the y actually. Not just one, in all directions. So how can I turn this into a function? The natural way is really to just consider, for example, okay, this part. So just consider this part of the graph. So if I consider this part of the graph and ignore all other, then for every x I have a unique value of y. Okay. So this is really the inverse trigonometric function actually. Each one of them, depending on what interval you choose actually. Okay. So out of all these slides, these curves, if you just choose, for example, only one of this, then this is the inverse trigonometric function actually. Okay. So you have, say for example, if you want to consider only this picture, then what is the domain of tangent inverse of x? Interestingly, its domain is entire line. So for each x you have, so the domain of this is entire arc. How about the range of it? The range, the values of y always sit between, what do you call these two numbers, minus pi by 2 to, okay. You may have, say, minus pi by 2 to pi by 2. So this should be really the range of it actually. Is it making sense? Yeah, really the tangent inverse x. And the same picture. How to differentiate tangent inverse x? So imagine I'm taking, say, y equal tangent inverse x, okay, and I want to compute its derivative, so I'm going to do the same. That, okay. So this is same as tangent y equal to x, and differentiate both sides with respect to x. So this is going to be secant square y, okay, and dy by dx, and this will become 1, and this will become d by dx of 1 over secant square y, but the secant square y is really, what do we call, cos cosine of a square, cosine of a square y actually. Okay. And if I want to write this in the terms of, for example, x cosine square y in the terms of x, then I need to write the cosine square in the terms of the tangent function actually. And how can we do it? I mean, you learned this in your metric and first year classes actually, that you can take any trigonometric function and you can express all other trigonometric function in the terms of that given trigonometric function actually. Okay. So how can I do it? Okay. So how should I begin? So say you take cosine square y. Okay. And I want to write it in the terms of tangent x actually, tangent y. So
सर वही लिखो sin square plus cos square equals to 1
okay.
और divide करा है cos square.
That's a good one actually. That okay, if you can do the then why we shouldn't just directly
Yes, we will directly
square
do
y.
that.
Okay, this is a good idea. Thanks for so sin square y plus cosine square y is 1. So if you divide everything by cosine square y, then this is going to be tangent square y plus 1 is secant square y, because this is going to be 1 over cosine square y, which is secant square y. So I don't need to really get into the cosine square y. And if this is the case, then secant square y can be directly written in the terms of the this. So it's going to be 1 over 1 plus tangent square y, and 1 over 1 plus and tangent y is x squared, so the derivative of this is going to be 1 over 1 plus x squared actually. So this is really is going to be the derivative with respect to dx of tangent inverse x. Okay, so that's how you can differentiate it. Okay, so finally, another interesting question that you can ask, or maybe you will encounter such kind of questions in your exercises, is that okay, if you have, for example, sine inverse not of an x, but you have a sine inverse of f of x. Okay, so in other words, you have sine inverse function composed with another function f of x actually. So how are you going to do it? So you're going to do this, that okay, take a function, say g of x, that is sine inverse x, then this function can be seen as a g composed with f of x. Okay, g composed with f of x. And how to differentiate a function g that is composed with f of x? So by chain rule, this is g prime, evaluate it at f of x multiplied by f prime of x. Okay, so this is what the recipe of it is. Then if alright, so if the g, so I need to do first what? By chain rule, you need to just compute g prime of x and then evaluate f of x into it. So if the g of x is sine inverse of x, so what would be g prime of x? So we know that this is going to be 1 over the square root of 1 minus x squared. While the g prime of f of x is going to be square root of 1 minus f of x plus. So this is going to be g prime of x. So hence, if you substitute this into this expression, so g prime of f of x is what? Is 1 over 1 minus f of x squared. Okay. 1 over square root of 1 minus f of x squared multiplied by f prime of x, so I can put an f prime of x here. Okay, so that's how you can compute the arc sine of any function. For example, if I give you, what is, and I just write directly on the same line, if you want to compute the cosine inverse of some function f of x, then take the derivative of the cosine function 1 over 1 minus x square, but on the place of x you have to replace f of x square multiplied by the derivative of f prime of x. So what would be, so this would be the derivative with respect to dx. What would be the derivative with respect to dx? of tangent inverse of some function of x. So for the tangent, we know the derivative is 1 plus x square, but the role of x is played here by f of x square multiplied by the derivative of f of x. So I can put in f prime of x actually. Okay, so try to drive by chain rule this similar kind of relationship actually. And if I give you, for example, say function, say y is sine inverse of say log of sine x. So you don't have to worry about this, that this is nothing but sine inverse is composed by log of sine x. So what would be the dy by dx in this case? We're going to say 1 over square root of 1 minus x square, but you have to substitute instead of x this log x, 1 minus log sine x square multiplied by the derivative of log sine x. So what would be the derivative of log sine x? Again chain rule, that because it is the composition of log function with sine x, okay, so it's going to be 1 over sine x times the derivative of the sine x actually, which is going to be cosine x, and you can simplify it, you can get what you call the result of it. So there are similar such exercises and given in your exercises, so you can use them, you can solve them, and have fun with those actually. Okay, so this is the last thing that we did from this. So Suleiman will upload really the exercises for you, and you can always ask a question on your WhatsApp group. We will also do after this, okay, uploading this and go through the all contents. We'll also do a Zoom session in which you can ask the question, okay, and maybe we can also discuss that whether doing things in this manner is better, or we do live, on Zoom sessions actually. But I think doing this is going to be, in my opinion, going to be a bit better, where you can. So one of the trouble with the Zoom is that there you can't write things in this manner on board actually, or on page actually. So you have limitations on Zoom. But another strategy that, for example, I'm thinking to follow is that, okay, we do the lectures in this manner, discussions in this manner, and then we have a discussion session over the Zoom actually. Okay, so I can have discussion session with Zoom, so Suleiman can have discussion sessions with Zoom, so we will be available for doing it. So let us know that whether this kind of strategies work or not for you. So we want your feedback. All right. So now I would like to move towards a very interesting application of derivative. This would be really the last thing in this chapter, number 4 on differentiation rules, and then we will move to the next chapter, which is really the derivative of the applications of the derivative actually. So this is what that we are having. All right. So, if you remember, we have discussed this a good amount of time, that if you have a curve, okay, and you are interested in, for example, computing this small quantity, okay, the length of this small quantity, then what you can do really is that, for example, I can draw a tangent line at one of the points, okay, and then I can approximate this part of the curve or the variation in this part of the curve by what do you call tangent line actually, because tangent line at a smaller level really approximates the given curve actually. Okay, so to make it kind of more concrete, let me start with a motivatory what do you call example. Now everyone knows that how to compute the square root of 4. Okay, everyone knows that how to compute the square root of 4. So we know that the square root of 4 is 2. Okay, but imagine you have to compute, for example, square root of 4.1. That would be so. You will wish actually that okay, not have this 0.1 actually. Okay, you can estimate that okay, if the square root of 4 is 2, so this is going to be 2 point something. But the question is that can you compute this without using calculator actually? So this is really the challenge actually. So you want to compute 4.1 and you don't have what do you call your calculator, then how you can compute it, or maybe the square root of 3.9 or something like that actually. Okay, so you are really close to some number where you know the thing, but you don't have calculator to compute it. So the derivatives are there to help you out in this case actually. So what we can do, so what is the general picture? So you will say that imagine I have okay, so I have say okay, so let me give you a general picture. So imagine you have a curve, okay, so this is your f of x, okay, and the value, for example, and this is say input a, and so this is going to this is really the corresponding output, or the output on the curve, or the point on the curve corresponding to this input. So the coordinates of this a and are going to be a and f of a. Okay, so what I'm interested in computing a value that is really near to this known point actually. Okay, so let's call this, if this is a, let's call this a plus what do you call h. Okay, so this is going to be a and f of a plus h. But how can I approximate it without, for example, using the function f of x? So what you can do is really that we know that draw a tangent line at, for example, point A, and this tangent line is going to really approximate the curve on, say, for example, on this small interval actually. Okay, so you have this small interval, okay, you have this small interval, and you can say that on this small interval the tangent and the curve are indistinguishable actually. They are one and the same actually. So can this help me out in order to know it? Then the answer is no, I guess actually. How can you do? So what can I think about is that okay, what is, so it's like you have a line, okay, and you have 2 points on the line, okay, so consider this, and the coordinates of, for example, this point, say a and f of a. The slope of this line, so let's call it m, and you want to know, for example, this point, so this a plus h and f of a plus h. So primarily I'm interested in this quantity f of a plus h. The question is if I have been given slope and if I have been given a point, can I figure out this f of a plus h actually? The answer is, it shouldn't be a big deal. What would be the equation of a straight line that passes through, for example, this point, okay? And then we know, I guess roughly I can say that f prime, so what would be the slope of this? I can approximate the slope of this by, say, f prime of a, that you compute the derivative of f prime of a, while the f prime of a can be computed as, f of approximately f of a plus h using these 2 points minus f of a, okay, and everything divided by what do you call h actually, and then you say that take h goes to 0, okay. So in other words, from this I can say that, okay, if I'm interested in computing f of a plus h, then I can do it easily by how? That you do the h, so I do f prime of a multiplied by h and add f of a into it actually. So this is really going to give me what we call an approximate value of f of a plus h actually. Okay. So if you want to know f of a plus h, then you need to know what is, the derivative at that point a, what is the value of the function at that point a, what is the slope of the tangent line at that point a, and how much you are going away from drifting from a actually. Okay, so how much you are going away from a actually. So this would be a useful trick actually. So how can I use it to, for example, compute this? Now I'm saying this, that take your function as a square root of x, for example, okay, and take a as, for example, 4. Then I know that f of a is 2. So what would be the derivative of, say, f prime of x? So it's going to be 1 over 2 square root of x actually, so I remember that you know that. And what would be the f prime of a evaluated at, for example, a actually? So it's going to be 1 over 2 square root of, what do you say, 4. So it's going to be 1/4 actually, okay? And what would be h? So h is really the difference. So if a is, 4, and a plus h is really 4.1 actually. The question is, what is h? So h is 0.1. So how much you are drifting away from a is really 0.1. And what does this immediately tells you? That using this information, now you can compute what you call square root of 4.1, because, or you can say that since f of a plus h is approximately f of a plus h multiplied by f prime of a, so I know all this stuff, so I can approximate my, so square root of 4.1 is approximately f of a in 2 plus h. I'm, how much is the difference between, your previous point and the new point. So the difference between the previous point and the new point is really 0.1. Okay, so 0.1 times f prime of a. So f prime of a I know is really 1/4 actually. Okay, so in other words, it's going to be 2 plus this actually. So what is going to be this value? So you can compute it. It's going to be 1/40. Okay, you can say it's 0.1 multiplied by 0.25. You can do your calculation without, calculator. This is not a difficult calculation using without calculator, and you can have an approximate value for what you call a square root of 4.1 actually. Okay, so what is the beautiful thing about this? So in other words, imagine if I say that I know that the sine of 0 is 0, but what about if I ask from you what is the sine of 0.1? Okay, so you can figure it out by using the same strategy, by detecting that your function is sine x, your a is 0 and your a plus h is 0.1. So using everything